right, so let's move quickly on this one. What's an LLM? So, we're on the subject of deep learning. Deep learning is a subfield of machine learning. It utilizes artificial neural networks, which is that graphic that you see there. This is called a perceptron. It's very simple. It's a simple general machine that can be used in a lot of ways. So a computer represents all data as numbers, right? That's the abstraction that a computer does. You have a picture, under the hood, the computer sees it as numbers. So each one of these blue circles in the input layer, if it's an image that you wanted to, an image of a cat that you wanted it to scan, and then at the end you want it to basically label it with the correct label of a cat, you got to break down that image into a set of numbers, and that's what the blue circles will take. And then it passes through these layers. All of my examples are like an egregious simplification of everything. What's cool about this is that it's very simple conceptually, but scale makes things so complex, right? Computers are simple, they're linear, but they're very complex. So I guess every time you see a graphic like this, just imagine a lot more layers. So this vertical column could be thousands and thousands of nodes or neurons. And then what's really good about these networks is that they self-learn, they self-improve over different cycles. So the information will pass left to right. And eventually it's going to be awful, like the outcomes are going to be terrible, but it uses this process called back propagation. This is the magic algorithm that updates all of the numbers that are associated with those lines. And that's essentially what's happening with these tools. Large language models it's a specific deep learning architecture or model that's designed to understand human language and generate more language. And they're huge. They're trained on massive data sets that we all know, mostly the entire internet. And the magic architecture that underlies all of the models that we have is the transformer. So this was a specific kind of architecture proposed by Google in the famous paper. And the key innovation with the transformer are these two blocks that you see that are sort of repeated. You have this attention block, which is this magic sauce ingredient, with the perceptron, the network that I showed you on the last slide. When you combine these two, this is where things that's why we had this rapid explosion of these tools since then, is that this really did kind of change things. Again, this is a simplification. These groupings of these two blocks, again, there's so many of them. And so here's a good illustration, right? Give it input text. So this piece of text is Wayfair is one of. At the other end, when it's all fine-tuned and trained, it's gonna give you that's literally all it does, is it give you the next token or text. You take that compound, Wayfair is one of and then it does it again, and then it predicts the next text, which is worlds. And it keeps going. That text goes in as the input. Wayfair is one of the world's largest, and you can imagine where that's going. Okay, so the training process is very interesting. There's a pre-training phase where this is where companies spend millions of dollars to train a model for a month, usually on an enormous graphic processor cluster in some data center somewhere. So models like Gemini are trained on the internet for the most part as unstructured data. These models don't store the literal information, right? It would be too big. So it compresses all of the knowledge into like pattern recognition. It's really interesting. And it stores these patterns as what we call weights. And I'll show you what that means. Weights are basically numbers again. Everything's a number at the end of the day, and they're tuned automatically by the model. This is the unsupervised learning. We don't know actually what they're doing. All we know is we see the input and the output, but they're doing it themselves, which is the freaky part. So at the end of this training cycle, what a company gets is basically a base model. A base model is a fancy autocomplete, right? All it does, which is still impressive, you give it some text and it will just keep generating more text. Post-training is interesting. This is where they fine-tune the model. This is where companies like sort of create, this is where they differentiate in a lot of ways. So they'll train the model on specific documents, even formatting. Like when you ask the model to give you like data back, it will give you a table sometimes. So it's like, this is how it knows how to do that stuff. It trains on these formats. And then they start training on conversations because it doesn't have that personality yet. So at the end of this process, companies get an assistant-like model. And then reinforcement learning is where a human comes in and is in the loop and will basically create like there's a reward structure where they'll signal that this was a good response, this one wasn't. And this is where you get personality and like ethical guidelines and human values into the model. So at the end of this process, you basically get like an aligned assistant-like model. All right, tokens and probabilities. We can do this. Tokens, numbers are the fundamental units of data. That's the raw material of these things. So everything that you pass into it as an input, whether it's an image, an audio clip, or text, will be decomposed into individual tokens. In a Wayfair analogy, if tokens is confusing, home-based text, image, color, and spacing tokens are the fundamental units of storefront experience designs. So we have an image, we have some audio, and we have some text. And this is like an illustration of the discrete translation of the data is into tokens. So I'm using color to show, these are the unique patterns that will be stored. That image is basically a bunch of little swatches or little tiles in these types of colors. Each color represents a unique token. All right, each token is represented as a unique number. Again, so we see text, but under the hood, the computer sees it as numbers. And these are unique IDs. So, and there's a finite set of IDs. So like, the dictionary, let's say, of the model is limited. So it might have 50,000 or 100,000 or 1,000,000 possible tokens to work from. GPT-4 has a finite dictionary of approximately this number. This is accurate of where I'm chopping up the text and how the computer sees it. And you might be wondering like why, Wayfair is cut up. There's actually spacing that is part of the token. And so it's like, why does it do this? Why doesn't it store individual characters like the alphabet? And the answer is simply like, it's too much of a load, too much computation cost to store individual letters. When you actually have chunks of words, you'll see in a minute that the compute is a lot easier because what it needs to do is basically make semantic relationships between these chunks. And it's faster for the model to be able to do it this way. All right, so we're going vertically. You can see how everything gets abstracted. Text turns into tokens. The tokens are represented as a single ID. And then these numbers are converted into vectors. And vectors is a mathematical topic. Basically, it's an array of coordinates. So you see these numbers, like the way is actually represented as these different dimensions. So the LLM will literally plot each token in a high dimensional space. So however many numbers there are in each array is how many dimensions the model is working with. So I don't know if you've ever heard that people say like, oh, like the models are thinking in this like super high dimensional space. It's true, this is how they do it. And what's really interesting is the proximity that they have to each other locally tends to have is where the meaningful relationships are. So if you have like the words man and woman, those vectors are actually going to be relatively close to each other in this space. And these vectors, these lines, these plotted points get fine-tuned and they get nudged and they get moved around as this network is training. So what happens when they first start predicting tokens and text, it's nonsense, it's gobbledygook. But over time, when this thing is rapidly training, these vectors are constantly moving around and optimizing, which is really, really cool to think about. All right, so it's all about the semantic relationship between these tokens. And like I said, it improves iteratively. So the weights, what I showed you is basically the data. The data are these vector arrays that get plotted, and the way that they get adjusted in that dimensional space is being multiplied against this other, it's called a tensor, when you have two-dimensional arrays. When it's just a lot of a matrix multiplication. When these numbers multiply against each other, that's how these vectors start moving closer or farther away from each other. It's very simple. So this is an illustration of the right column is a token, and it's getting multiplied against these fine-tuned weights. And these numbers basically are the secret sauce to all of the company's models. These numbers are worth millions of dollars, and there's a reason why companies don't publish these tokens. It's because this is where the value is, these numbers. All right, how tokens get generated. At the end of each token prediction cycle, the model calculates a probability distribution. This is really interesting too. So of all possible words that are in the model, the dictionary that we're calling, let's say it's 50,000 possible tokens that it could be. The model rolls dice. It basically assigns a probability of what word would get sampled. Sampled is a word that's used for picked. And here's an example. So Wayfair is one of the world's largest, and it's about to predict the next token. And you can see I've sorted the most probable next token to the least probable. And it's you can see it's just 3 Z's. Like that could be a token in the dictionary, and there's a 0% probability of that one getting predicted. Then home is the most probable next token. Online, e-commerce, retail. These all sort of make sense to be next possible tokens. So this is kind of like shocking, where it's like the model's literally throwing dice. It's a random generator for the next token every time. So most of the time, the token with the highest probability will be picked. But if you run this process many times, like it does, once in a while, the token with a lower probability will be picked too, right? That's how rolling the dice works. And that's why a model could respond differently when you ask it the same questions multiple times, is that it's going to sample something else. It might sample retail instead of home or e-commerce. And again, it all depends on the context before the first word, Wayfair, as well. That's how it picks as well. All right, so let's get into that is like the default state of it. It can sample from any of these tokens in the dictionary, but we have control over how it actually does this. And I'll show you how to do this in Gemini. So we have some settings that we can control. So we have top K, top P, and temperature. And a Wayfair analogy for top K and top P can be thought of as like these are a set of catalog search filters, right? You have a set of product and you want to filter them, top P and top K. The naming sucks because the letters K and P come from like the statistical discipline, but K, I try to curate my own mnemonics to remember things. I think of kin, like top kin. It's like of all the possible children, I'm choosing just these as my top children in the whole pool of children. So what we're looking at by default, right? It could sample any of the 50,000 tokens and assign a probability. But I want to control that. I want to control the number of tokens in the sampling pool. In this example, out of the pool of 50,000, I'm going to move the slider to 1,000 tokens. So all of a sudden, I am filtering to the top 1,000 tokens. Top P controls the total probability distribution. So when you have a probability distribution, everything has to basically add up to 1 or 100% and has to be distributed. And by default, usually it is at 1. So, but you can control this. You can move the slider. Let's say I want to distribute 10% probability. So this is interesting. So based on that number, it needs to add up to 10%. So it's going to try to pick the most probable token first. So it says, all right, I have this one in my choice pool. Now I need to basically fill the rest. So it looks for how to add up to 10%. And you can see how it got to 10% here. So it's actually going to likely sample from either home, destinations, or stores. So this is like a very, very specific way to sort of like get control over how it samples. Temperature is the one that you're probably going to use the most. And like if you're a copywriter doing marketing copy, or like you're writing song lyrics, this is a good control to sort of use. So basically, by default, it will be at 1. And this is the typical distribution that we had by default, where, again, home is the most probable. If you do a low temperature, it basically does a non-linear scaling where it favors the most consistent, the most deterministic, the most expected choice or sample. And so if you're doing math or coding, or you don't want a lot of randomness, then this is what you want to do. If you want the opposite, if you want it to be more creative, more diverse, more random, then you do a high temperature. And it does a non-linear scaling of all the distributions. So you can see that it increases all of the lower ones, and it actually reduces the ones that are more probable. So I did an experiment here. I wanted to see what happens if I did a low temp prompt and a high temp prompt. This is the famous crawl from Star Wars. And I wanted to see if it could predict the rest of the text. So I asked it to complete the text. A long time ago in a galaxy far, far away, it is a period of civil war, rebel spaceships striking. I did low temperature, and then I did a high temperature. This is the results. So low temperature, it nailed it. It said, striking from a hidden base have won their first victory against the evil galactic empire. The high temperature one was funny. It said, rebel spaceships striking from the edges of the galaxy attack the empire's pleasure cruisers with laser fire. So again, if you wanted something more creative or even humorous, this is how you get that. So you will find there's a lot of documentation out there on techniques. So very simply, there are these like 0 shot, 1 shot, few shot prompts. 0 shot is when you give it no examples. It's like you're throwing a Hail Mary sometimes, and this input can be anything like a question or a set of instructions. 1 shot prompt is giving it 1 example. It gives it example for it to imitate. A few shot prompt is when you give it a few examples. So you want to make it very clear that you have a clear pattern in mind that you want it to follow. And then there's a system prompt, which I'm actually going to get into for my first use case. This is the initial prompt that defines the overall purpose for what the model should be doing. Gemini gems is a good example of this. When you have something that's repeatable, you want to create a gem. All right, so I'm going to jump over to Gemini. Take a look at my gem. All right, so the obvious one that came to mind was like, I need a web accessibility expert, right? So as I'm designing UI, I need to keep in mind, like what's the accessibility guidelines I should keep in mind. Constantly Googling. So I'm like, I'm gonna create a gem. So you can steal this from and see how it works for you. Because I know that a lot of us are in the same boat, but I'm basically, again, I'm iterating constantly, right? I'm iterating in the instructions that I want to give it, and I keep testing it and coming back here. So I've set up a role. I want you to be an expert consultant, specifically for WCAG 2.2 level AA compliance. Here are your behaviors and rules. If the question is unclear or you're unsure how to answer it, like, I want you to come out and just say it. Like, I don't want you to hallucinate on me here. Always reference 2.2 documentation, not 2.1. Very specific about that. And provide relevant success criteria. Like, I want to know, what do I need, where do I need to be in order to consider it like successful, to achieve that conformance. And then tone, maintain a helpful, informative, professional demeanor, clear language, avoid responding with unnecessary patronizing language. I get annoyed by this sometimes, where it's like there's a lot of filler copy at the beginning and the end, where it's like, hey, great question. It's like, I don't want any of that. Avoid follow-up questions at the end of your response. I don't need any of that. So this is the areas where I'm fine-tuning. And there's another setting with models that you can actually control how many tokens get outputted. So if you want stuff that's really tight, you can actually do that. All right, so an example was, I was interested in finding out about requirements for line height values. Is there a conformance guideline that we need to have? And it did pretty well. So what's really nice about these models now is that they give you citations, so I can clearly see where it's referencing, and it is pulling from the 2.1 document, 2.2 documentation. And it very clearly says that it's a nice to have, and these are the suggested values. So yeah, if you want something like this, like, please just copy my template and then iterate on it if you feel like it should be doing something else.